In the realm of data science, tabular data imputation is a pivotal task that significantly influences dataset quality. The absence of values can drastically affect analysis outcomes. To address this issue, various methods have been employed, including statistical algorithms, shallow machine learning algorithms, and deep neural networks. However, deep generative model-based imputation models, particularly diffusion models, have shown competitive performance in modeling the data manifold and completing missing elements. These models have demonstrated remarkable capabilities in generating data across diverse types, such as images, audio, and time series data. Recent studies have applied diffusion models to tabular data generation and imputation tasks. Nevertheless, vanilla diffusion models are suboptimal for tabular data imputation due to two key mismatches: objective mismatch and data scale mismatch. The objective mismatch arises from the inherent difference in learning objectives between generation and imputation problems. Specifically, diversity is a key aspect in generation tasks, whereas imputation tasks prioritize accuracy and consistency. This mismatch can severely impede the imputation performance of diffusion models. The data scale mismatch is attributed to the natural sparsity inherent in the tabular domain, which poses challenges for diffusion models. The sensitivity of diffusion models to initialized noises further exacerbates this issue, impacting the robustness of these models for data imputation. To address these challenges, this research proposes an advanced diffusion model, Self-Supervised Imputation Diffusion Model, SimpDM, specifically tailored for tabular data imputation tasks. SimpDM introduces a self-supervised alignment mechanism to regularize the model, ensuring consistent and stable imputation predictions. Additionally, a carefully devised state-dependent data augmentation strategy is employed within SimpDM to enhance the robustness of the diffusion model when dealing with limited data. The proposed model aims to mitigate the sensitivity to noise and improve the imputation performance of diffusion models. Extensive experiments demonstrate that SimpDM matches or outperforms state-of-the-art imputation methods across various scenarios. The research highlights the potential of self-supervised learning in improving the performance of diffusion models for tabular data imputation tasks. The proposed model is formulated as follows. The self-supervised alignment mechanism is designed to regularize the model, ensuring consistent and stable imputation predictions. The state-dependent data augmentation strategy is employed to enhance the robustness of the diffusion model when dealing with limited data. The research provides a detailed analysis of the proposed model, including its architecture, training process, and experimental results. The results demonstrate the effectiveness of SimpDM in improving the imputation performance of diffusion models for tabular data. In this research paper, the authors address the challenges faced by diffusion models in solving tabular data imputation tasks, particularly the mismatch between the objectives of data imputation and generation, as well as the limited data scale. They propose a novel diffusion model called Self-Supervised Imputation Diffusion Model, SimpDM, which integrates two effective techniques: self-supervised alignment and state-dependent augmentation. The proposed method aims to enhance the accuracy and stability of imputation results. The authors identified two key challenges that hinder diffusion models in tabular data imputation tasks: target mismatch and data scale mismatch. Target mismatch arises from the difference in objectives between data generation and imputation, with the former focusing on generating diverse samples and the latter aiming for accuracy. Data scale mismatch occurs due to the smaller size of tabular datasets compared to other domains, making it difficult for diffusion models to capture the true data distribution. To tackle these challenges, the authors introduce a self-supervised alignment mechanism to regularize the output of the diffusion model, encouraging consistent and accurate imputation for the same observed data. Additionally, they propose state-dependent augmentation, a perturbation-based data augmentation strategy designed for tabular data imputation tasks. This strategy extends the training set, improving the robustness of the diffusion model and enhancing the effectiveness of the self-supervised learning framework. The authors also provide a brief overview of related works in tabular missing data imputation and diffusion models. They highlight that early solutions use statistical algorithms and shallow machine learning methods, while recent studies leverage deep learning techniques, including deep neural networks and generative model-based approaches. However, they note that these approaches often underestimate the disparity between data imputation and generation, leading to suboptimal imputation performance. The proposed SimpDM model is evaluated through extensive experiments on 17 benchmark datasets across multiple missing data scenarios. The results demonstrate the strong imputation performance of SimpDM compared to state-of-the-art methods. The contributions of this paper include identifying the challenges faced by diffusion models in tabular data imputation, proposing a novel diffusion model to address these challenges, and verifying the imputation capability of SimpDM through empirical studies. Diffusion models have demonstrated significant success in generation tasks across various domains, including images, text, audio, time series, and graphs. Recent studies have sought to leverage diffusion models for learning tasks on tabular data, with methods such as TabDDPM, CODI, and STASY showing impressive capabilities in tabular data synthesis. Inspired by the success of diffusion models in image inpainting and time series imputation, researchers are now exploring their potential in tabular data imputation. The paper defines the problem of tabular data imputation, where a binary mask matrix M represents the missing data, and the goal is to estimate an imputed data matrix X that fills in the missing entries of X. The authors introduce diffusion models, which are deep generative models derived from a forward and reverse Markov process. The forward process gradually disturbs a sample X0 into a noisy sample XT, while the reverse process denoises and generates the sample X0 from XT. The paper explains the evolution of the distributions using forward and reverse process equations, and describes Gaussian diffusion models, which have forward and reverse processes characterized by Gaussian distributions. The authors also introduce multinomial diffusion models, which define a categorical distribution that perturbs the data with noise over k-classes. The paper then presents the methodology of SimpDM, a self-supervision improved diffusion model for tabular data imputation. The overall training pipeline of SimpDM is demonstrated, including the base diffusion model constructed for tabular data imputation, and two pivot designs: state-dependent self-supervised alignment and data augmentation. The authors discuss how to apply SimpDM to mixed-type tabular data, and introduce modifications to adapt the diffusion model effectively for tabular data imputation. The proposed SimpDM model pipeline is a novel approach to tabular data imputation, leveraging a Gaussian diffusion model for accurate and efficient missing value estimation. The training process begins with average padding of missing entries in the input data, followed by the sampling of a pseudo-missing mask and a condition mask. These masks are essential for the self-supervised alignment step, where the model is trained on two channels with different t and epsilon values. This step calculates both the diffusion model loss, L_dm, and a self-supervised alignment loss, L_SAW, which aims to minimize the distance between predictions from the two channels. A key innovation of the SimpDM model is its state-dependent augmentation strategy, which perturbs the model's input based on the state of each entry ground truth, GT, model sampled, MS, or pseudo-missing, PM. This hybrid input design allows the diffusion model to effectively utilize known information to infer missing data while maintaining consistency across different samples in the input space. The diffusion model architecture is based on a plain multi-layer perceptron, MLP, eliminating the need for a U-net architecture or cross-layer shortcut. This design reduces computational cost and prevents overfitting. The learnable embedding of the diffusion step T is added to the latent representation at the first layer, and a learnable projection layer maps the missing mask vector to a mask embedding, which is then added to the first layer latent representation. This enables the diffusion model to discern the status of the hybrid input and make accurate imputations. To address the challenge of unknown ground truth values for missing entries during training, the SimpDM model employs a pseudomissing training strategy. The model pads missing entries with column-wise average values, samples a pseudo-missing mask, and merges it with the original missing mask to create a condition mask. Gaussian noise epsilon is added to entries where the condition mask equals 1, and the model is trained to denoise the pseudo-missing entries. The model predicts the ground truth values of missing entries, and the loss function is calculated solely on the pseudo-missing terms, directing the model's attention toward completing the missing data. The training process of the Gaussian diffusion model for tabular data imputation is encapsulated by the loss function L_dm, which computes the mean squared error between the ground truth values and the model's predictions. The model input x_t is a hybrid of the original input x_0 and the noisy input x_t, combined using the condition mask m_c. This innovative approach has significant implications for improving the accuracy and efficiency of missing data imputation in tabular datasets. In the context of tabular data imputation, the proposed model, SimpDM, introduces a self-supervised alignment mechanism and state-dependent data augmentation to enhance the performance of diffusion models. This setup utilizes two parallel channels with shared pseudo and condition masks, generating hybrid inputs for the diffusion model. An alignment loss is minimized to enhance imputation performance by reducing the difference between outputs from these two channels. To address the issue of limited dataset size and potential overfitting, a state-dependent data augmentation strategy is proposed. This method perturbs entries based on their certainty levels, allocating higher perturbation strengths to entries with lower certainty. This approach increases the robustness of the model and facilitates self-supervised learning by amplifying data diversity across the two channels. The paper also discusses extending SimpDM to mixed-type data, introducing a multinomial diffusion process for categorical features and keeping the Gaussian diffusion process for numerical features. Categorical features are assigned a k-dimensional prediction head followed by a softmax function, with cross-entropy loss used for optimization. For self-supervised alignment, the authors minimize the output scores of each prediction head. Random state transformation is applied as perturbation for categorical data in state-dependent data augmentation. This research paper presents a comprehensive evaluation of various missing data imputation methods, encompassing both shallow and deep learning techniques. The study leverages 17 real-world datasets from the UCI Machine Learning Repository and Kaggle, spanning diverse domains such as housing, diabetes, and energy. The performance of these methods is assessed using root mean squared error, RMSE, providing insights into their strengths and limitations. The proposed method, SimpDM, is benchmarked against three groups of baselines: shallow methods, including mean imputation, k-nearest neighbors, KNN, misforest, and multivariate imputation by chained equations, MICE, deep methods, comprising optimal transport, OT, miracle, grape, and iterative Gaussian regression model, IGRM, and deep generative methods, including MIWAE, generative adversarial imputation network, GAIN, tabular conditional sequential density imputation, TAB-CSDI, and forest diffusion. Experimental results demonstrate that SimpDM outperforms most baselines in terms of RMSE, showcasing its effectiveness in handling missing data. The evaluation is conducted under a missing completely at random (MCAR) scenario with a 30% missing ratio, and the average test accuracy over 5 runs of experiments is reported. Hyperparameters are selected through grid search, with detailed information provided about the search space for these parameters. The computing infrastructure used for the experiments features a 4-core CPU, 16 GB memory, and an NVIDIA T4 GPU with 16 GB GPU memory. The source code of SimpDM is publicly available, ensuring reproducibility and facilitating further research in the field. SimpDM's performance is compared to various baselines in Table 1, showcasing its adaptability and robustness in addressing missing data imputation challenges. Notably, SimpDM outperforms all baselines on 11 datasets and achieves runner-up results on the remaining 6 datasets, underscoring the effectiveness of self-supervised alignment and state-dependent augmentation. Compared to diffusion model-based methods, such as TAB-CSDI and FD, SimpDM exhibits significantly better performance, highlighting the potential of self-supervised alignment and state-dependent augmentation in addressing imputation problems. Among generative methods, diffusion model-based approaches perform slightly better than GAN, VAE-based methods, demonstrating the potential of diffusion models in addressing imputation challenges. Deep learning-based methods, including Miracle, Grape, and IGRM, show competitive performance, highlighting the superior capability of deep neural networks in data completion. In contrast, shallow methods, such as KNN and MF, exhibit strong performance, underscoring their superior capability in tabular data imputation. Notably, SimpDM requires less memory compared to the strongest baseline IGRM, indicating its efficiency and scalability. To investigate SimpDM's generalization ability in various missing scenarios, experiments are conducted on different missing scenarios, including missing at random, MAR, and missing not at random, MNAR, in missing ratios. The results, presented in figures 3 and 4, demonstrate that SimpDM consistently surpasses all representative baselines in both scenarios, highlighting its robust generalization capabilities. Ablation studies reveal that both self-supervised alignment and state-dependent augmentation yield substantial performance enhancements for the base model, with self-supervised alignment demonstrating a more pronounced impact on performance across the majority of datasets. Experiments evaluating the effect of different self-supervised losses, including MSE loss, contrastive loss, and Sinkhorn divergence, are presented in the appendix. The results evaluate the respective effectiveness of these losses in eliminating the unexpected diversity of imputation results. Furthermore, experiments conducted on different missing ratios, presented in Figure 4, demonstrate that SimpDM consistently exhibits optimal or competitive performance across various missing ratios. Notably, in situations of severe data absence, SimpDM exhibits more substantial performance gains compared to the deep baselines. Overall, the results highlight the effectiveness of SimpDM in addressing missing data imputation challenges, its adaptability and robustness in various missing scenarios, and its efficiency and scalability compared to existing baselines. The authors evaluate their proposed diffusion-based model, SimpDM, for tabular data imputation through an ablation study. They assess the effectiveness of key components, self-supervised losses, and augmentation strategies. The results show that integrating self-supervised alignment and state-dependent augmentation improves imputation performance, with SimpDM achieving the best results on most datasets. The impact of different self-supervised losses, including contrastive loss, skip connection loss, and mean squared error loss, is also investigated. The results indicate that mean squared error loss performs optimally on 7 out of 8 datasets, while contrastive loss and skip connection loss also yield improvements. Furthermore, the authors examine the effect of different augmentation strategies, including strong, weak, and state-dependent augmentations. State-dependent augmentation is found to be the most effective, as it applies customized perturbation strengths to each entry according to its state and certainty. A runtime analysis demonstrates that the training time of SimpDM exhibits a linear relationship with both the number of samples and the number of dimensions, indicating high running efficiency and scalability. The experimental results show that the training cost of SimpDM is relatively small. A qualitative analysis, including a case study and visualization, provides further insights. The case study demonstrates that SimpDM yields stable and accurate imputation results from diverse initial noises. The visualization reveals a significant overlap between the distribution of data imputed by SimpDM and the original data distribution, suggesting that SimpDM effectively captures the data manifold. Overall, the authors provide comprehensive empirical evidence to support the effectiveness and efficiency of SimpDM for tabular data imputation. Researchers have developed a self-supervised alignment mechanism to enhance diffusion models for tabular data imputation, tackling sensitivity to noise and discrepancies in data scale. This approach, termed SimpDM, is outlined in 2 algorithms. Algorithm 1 governs training, where a pseudo-mask is sampled, and the diffusion model is run on 2 channels. The diffusion model loss and self-supervised alignment loss are calculated, with the latter computed using the mean squared error between imputed data from both channels. Algorithm 2 facilitates imputation by initializing inputs with random Gaussian noise and recursively running denoising iterations with the diffusion model. Observed entries are set to ground truth values before each denoising step, ensuring observed values guide the imputation process. Notably, SimpDM's time complexity scales linearly with both the number of samples and dimensions, with a training phase complexity of O, NDH, D plus DHL, and a testing phase complexity of O, NDT. Experiments were conducted on 17 datasets from the UCI Machine Learning Repository and Kaggle, featuring varying sample sizes, numerical features, and categorical features. These dataset statistics are provided in Table 5. The results demonstrate the superior performance of SimpDM across various scenarios, highlighting the effectiveness of its self-supervised alignment mechanism and state-dependent augmentation strategy in improving diffusion models for tabular data imputation. Data imputation is a crucial task in handling missing values in real-world datasets, where missing completely at random, MCAR, missing at random, MAR, and not missing at random, NMAR, mechanisms pose significant challenges. Diffusion models, initially applied to image synthesis tasks, have shown promise in addressing these challenges. These models rely on score functions, which measure the similarity between two probability distributions. By adapting diffusion models for tabular data imputation, researchers can leverage techniques such as denoising diffusion models and score-based diffusion models. The choice of noise schedules is critical in training these models effectively. Conditional score-based diffusion models can be applied to time series forecasting, where temporal dependencies are essential. Geometric diffusion models have also demonstrated potential in molecular conformation generation, showcasing the versatility of diffusion models across domains. A comparative analysis with state-of-the-art imputation methods, including traditional statistical methods and deep learning-based approaches, highlights the advantages of diffusion models. These advantages include handling mixed-type data and providing uncertainty estimates for imputed values. In contrast to traditional methods, diffusion models can capture complex relationships between variables and provide more accurate imputations. The paper emphasizes the need for more robust evaluation metrics to assess the performance of diffusion models in data imputation tasks. Future research directions include integrating diffusion models with other AI technologies, such as generative models and reinforcement learning. By exploring these avenues, researchers can further enhance the capabilities of diffusion models in handling missing values and improve the overall quality of imputed data.